My name is Mike Williams. I work at a company called Fast Forward Labs, which does sort of applied research into statistics, machine learning, things like that. So I'm not really a visualization person, but I'm going to talk about how we visualize text today. We do applied research, and we share that research with our clients, their banks, publishing companies, some startups, and we build prototypes that go along with a book essentially explaining an algorithm or whatever. I'm going to show you a couple of those prototypes later today. One of our recent projects was on text summarization, so taking a long document and making it shorter. And that got me thinking about how we visualize text. This talk, the jumping off for this point is word clouds. Word clouds are supposed to give an idea of the themes in a document. I'm going to argue in a second that they do so extremely poorly. They are at best, though, quick and dirty, so they do serve a need, so we need something that perhaps isn't quite so quick and quite so dirty, that allows us to explore the themes of a document, maybe compare two documents. I'm going to talk about a couple of approaches that point in that direction. Like I said, I'm not a visualization person. What I'm going to be talking about is algorithms that perhaps are the foundation stone of new kinds of visualizations. I'll show a couple of proof of concept visualizations, but I guess one of the reasons I'm here today is I want to get the visualization community interested in these approaches. I should say, by the way, that visualization is not the only use for these algorithms. One of them I'm going to talk about is something called recurrent neural networks, which are kind of the new hotness in deep learning. They're used to make breakthroughs right now in things like machine translation, conversational AI, speech generation, all that stuff. But today's focus is visualization. So this is a word cloud, and I'm so sorry. So this is a word cloud someone made about Strata last year. Strata is a big data conference that happens up the road at the Javits Center every year. And I'm showing this word cloud to make 2 points. The first is we can use this word cloud. We can use it to see there's a vast amount of infrastructure. There are huge numbers of very sophisticated technologies for distributed compute, distributed storage, that if you have an algorithm and the data and the AWS or Domino budget or whatever to analyze that data, then you're in business. The problem is, and this is the second thing we see from this word cloud, we don't have the algorithms for text. This is word salad. This is gibberish. It has 2 problems. The first problem is related to the algorithm with which it begins. The second is a problem to do with the actual visualization strategy. So first I'm going to talk about the algorithm. It doesn't take long to explain what I want to say there. The algorithm begins by splitting the document up into words and counting the occurrences of each word. It might do something a little bit more sophisticated after that, like considering term frequency, inverse document frequency, or whatever. But the basic idea is it's counting words. That is an extremely crude approach that mangles the meaning of a document. Do you necessarily care which is the most commonly occurring word in a document? A document is not a collection of words, it's a collection of ideas. This doesn't tell you about the ideas expressed in, I guess these were the titles of the talks. It tells you something much, much glibber and shallower, which is word counts, which is a programmer's idea of meaning. You certainly can't reform the original document from this visualization, and that's lossy compression for you. That's par for the course. I'm not necessarily going to suggest visualizations that allow you to do that, but the extent to which you are running the document through a blender before visualizing it is a clue to the problem here. So we can say what words were important, assuming your definition of importance is that it was mentioned often, but we can't say what ideas are important. I'd also argue, and this is the second problem, that we can barely say what words occur frequently, and that's a problem associated with the visualization strategy used here. And I'm going to spend some time on that before I go back to the algorithmic problem and solutions to that algorithmic problem. So the visualization problem is, I think, quite well known. It's the same problem that pie charts suffer from. This is an image I stole from someone's Twitter account earlier this year who then deleted the tweet because it resulted in an extremely long conversation of like bike shedding and arguing about pie charts. But these 3 pie charts, we're going to have the bike shed conversation now, I'm afraid. These 3 pie charts are very similar, right? I assume you'd agree they look superficially very similar. If I visualize the data now in this way, you can see they're actually very different sets of data about very different situations. So, I mean, it depends on what X and Y are here, but let's say X is time, it's financial quarters or something like that, and Y is revenue. Situation A, B, and C are very different if you're the CFO of a company. One of those is things are going well, one of those is things are going okay, and one of those is things are going badly. Those mean different things. And if all I've given you is the pie chart, you're not going to be able to make that distinction. The information is there in the pie chart. Those pie charts aren't buggy. They do have the information in them. The problem is we as a species are just crappy at doing the thing these pie charts require you to do, which is to compare the areas of physically dislocated objects that are different shapes. These triangles are dissimilar in the mathematical sense. They're not the same shape, and that's an extremely challenging thing for a human to do. We can make it easier. I don't want to rag on 538. The previous talk was excellent, but I do want to criticize this visualization. We can make it easier by asking you to compare identical shapes. The way you interpret this visualization is by comparing the sizes of circles. This is a visualization of the number of field offices Trump and Clinton had in various states in the United States. And all you have to do is compare the circles to say who had the bigger field operation. So I'm going to illustrate that this is a bad visualization, or at least a visualization that doesn't allow detailed quantitative analysis, by asking you a couple of questions. So the first one is, did Trump have more offices in Arizona, Nevada, or is that Nevada? That is Nevada, or Colorado? Which of those three red dots is biggest? That isn't a hard question because you're sat at the back. It's a hard question right here on my screen as well. It's a difficult question to answer. And I could make it easier by asking about states with bigger operations. So if I asked you to compare, what was it? Let's say Virginia and Iowa. There's Iowa and there's Virginia, Clinton's operation there. Which of those two blue circles is bigger? Again, it's a hard thing to do. And this is the easiest possible question I could ask. Which of these circles is bigger? If I turn it into a quantitative question, it becomes pretty much impossible. So if I ask you to say, let's say, what's the question? How many times more offices does Clinton have than Trump in Pennsylvania? If I ask you to do that, we'll be here all day. It's an extremely hard question to answer. That's not just because we're bad at perceiving area. It's also, despite the key here, and I've been looking at this chart for a long time, I'm still not clear on whether it's using area or radius as the measure of the size of the operation here. So, and this is about as easy as these kind of area-based plots get. Sometimes we make them hard, though. This is a famously dishonest and bad pie chart. The green here, the green wedge here is Apple's share of the smartphone market back in, I don't know, 2008 or something like that. And the purple there is other. And you can see something's gone wrong here, and that's the fact that we've made it into a 3D pie chart, which is sort of the platonic ideal of a bad data visualization. The reason it's a bad data visualization is it asks you, the user, to do something incredibly difficult, which is deprojection. We're asking you to deproject a two-dimensional image in your head into a three-dimensional image and then compare volumes. Now, I did a PhD in astrophysics, and what I was doing there was deprojecting galaxies. So galaxies appear at random orientations. You have a flat image on the sky, and my job was to figure out what they actually look like in a 3D sense. I don't want to suggest my PhD was particularly hard, but it did take me 5 years. And I would submit, if we're asking users to do with visualizations something that in other circumstances we'd give out a PhD for, we're asking too much. So that's the problem with pie charts. I think it's fairly well understood, but I would argue that word clouds share all these problems. So if I ask you to say, is one word more common than the other? I think what you're supposed to do is compare font sizes. You're supposed to compare the vertical height of these words. So you're supposed to try and ignore the width, because that's just an artifact of how long the word happens to be, and just compare vertical height. But we've built a visualization, and the human perception system is set up to be drawn to words that are large in area, or perhaps not even large in area, but large in terms of amount of ink on the page. And again, that's just a function of whatever letters happen to be in the word. Some letters contain a lot of ink. Whichever is the right thing to compare, height or some other linear dimension or area or ink, it's a very hard thing to do once you know which one is the right thing to do. Anything except the crudest, biggest difference, like Hadoop at the bottom and big data at the top, that's easy. But as soon as you get into anything interesting, anything other than the glibest, most superficial comparison, it becomes extremely hard. So the reward for doing something extremely hard visually with your perception system is an extremely crude, glib analysis. And the isolated word cloud also raises the question, compared to what? So in this visualization, is Hadoop being talked about a lot? I mean, it depends. I mean, what do you mean compared to last year, compared to another conference, compared to a corpus of books that, O'Reilly publishes or something? So that brings us to a more fundamental problem with word clouds, which is that data is completely decontextualized. And the only way to contextualize a word cloud is to show another word cloud. And now you've got two problems. So this is great data. This is data from the World Wellbeing Project at Penn. And this happens to be a comparison of use of language on social media. They collect a huge data set and slice and dice by demographic attributes. And in this case, I don't know if you can guess, but it's female on the left and male on the right. And there is an at-a-glance comparison you can make here, but it's at the level of men talk like that, women talk like that, of crappy stand-up comedy. This is not analysis of a rich data set, or it is a rich data set, but the visualization does not enable that. You can see at the bottom, I don't know if you can read, there are keys there that show there are multiple dimensions in this data set. Good luck parsing those dimensions. And so I know this is kind of money for old rope, but I'm going to quote Edward Tufte here. The only worse design than a word cloud is several of them. So hopefully the word is out and word clouds are bad. The visualization itself is hard to use, and the reward for that hard work is an extremely glib comparison, and perhaps not even a comparison. And that's because we've mangled the ideas by cutting things up into words and counting words, which is not how we think about documents as humans. So we'd like to move away, and it seems like people have got the message, but what do we replace them with? They serve a real need. So I'm going to talk about two options. Like I said at the start, these are algorithmic approaches. These are not visualizations yet. So I don't mean to say these are better than word clouds. That would be an apples and oranges comparison, although they are better than word clouds. But I do think they point the way to future approaches. So firstly, let's talk about topic modeling. In a word cloud, the first thing we do is count words. Topic modeling as a visualization strategy replaces that by looking at the relative importance of topics rather than raw words. What does that mean? What's a topic? Well, in topic modeling, a topic is a collection of words that tend to co-occur. So if you pick up a copy of the New York Times, words like president and Congress and election tend to co-occur in the same article. Organism and DNA and gene tend to occur in different articles. This matches what we mean in normal conversation when we say topic. But the advantage of this formal definition of co-occurrence of words, it means you can bust out the big guns of Bayesian inference and learn these topics from a corpus of documents that matches the kind of documents you're working with. So let's say I have a corpus of New York Times articles dating back to 1900. I can run topic modeling on that and learn which topics are important in that corpus. That's topic modeling. It's a standard algorithm. The standard way of doing it these days is with an algorithm called latent Dirichlet allocation, which is available. There's a topic models package in R. It's in like every other machine learning library in Python as well. I'm happy to talk about the details of those different implementations later. But this is a cartoon. So what do the real results look like? This is a topic model of the reviews of books on Amazon. I ran this, I fitted 100 topics. These are the first 12 of about 2 million books on Amazon. And you can see real collections of words that match what we mean by topic. Topic 0, sorry for the R people, we start counting at 0 where I'm from. The first topic there is cookery, obviously. Second topic is the wizard, Harry Potter, prisoner of wizard, whatever stuff. And it goes on, and you can imagine assigning labels to these topics. 11 is your Twilight topic. Interesting, I just want to draw your attention to number 4, which is a topic not like the others here, which is not the genre of book. It's a topic about the quality of writing. And that's because we haven't run the topic model on the books. We've run it on the reviews. And in the reviews, people talk about whether the writing's any good. So we've learned a custom topic model for this kind of text. What do we do with that? Well, we use it as the lens through which we look at any future document. So we take an individual document, say back to the New York Times articles. We take a new New York Times article, and we now look at to what extent these 100 or whatever topics are represented in that document. So here we've got a document that is 50% the politics topic, 30% computers, 20% genetics. And we could build something that allows us to visualize this quickly. I mean, there's a cartoon of the most obvious thing you could do here, which is a bar chart. If you have 100 topics, that starts to be a problem, but you can imagine approaches that might work around that. Why is this any better than a word cloud? In a word cloud, we are saying the word president occurs a lot, or the word DNA occurs a lot. Here we're saying the word, the politics topic occurred a lot, or genetics topic occurred a lot. Well, for one thing, there's relatively few topics compared to words. A news article might have 1,000 unique words. A longer document might have 10,000 unique words. You certainly can't plot a bar chart of that, which is why we're reduced to doing things like a word cloud, and not only doing things like a word cloud, but throwing away all but the top 20 or 50 words, because otherwise it becomes completely unwieldy. We've scaled the problem down. We've compressed the document in a semantic way, in a way that's driven by the meaning of the document, that allows us to reduce it to 100 or so numbers. And now we've got the more familiar toolkit of data visualization available to us, things like bar charts, stacked area graphs, things like that. But there's a more important advantage to this approach over word clouds, which is that the topic encodes a more meaningful semantic unit. A word cloud, for example, considers film and movie to be different words. And of course, they actually are different words. But from the point of view of learning about the ideas expressed in a document, do I necessarily care about the difference between film and movie? Probably not. So this approach gives us access in a data-driven, like unsupervised machine learning way to these themes. We don't have to go through and read the New York Times back to 1900 ourselves. We don't even have to understand the language our corpus is written in. The unsupervised machine learning will learn the topics for us and then express the documents in this way. So this is kind of a cartoon of a visualization option. This, I think, is an option that goes too far in the opposite direction. This is PyLDAViz. There's an equivalent called LDAViz in R. And this is for exploring topic models. I'm happy to show a live version of this to anyone. You can click on these circles, and it'll tell you what words are in the topic. This is a fantastic tool if you're a developer of topic models for debugging and figuring out what's going on with your topic model. I would argue this is not something you want to show to an end user. So what's perhaps a more humane alternative? And I mean humane in the design sense, humane and centered around the way a user thinks about a document. Here, I would argue, is an option. This is a summary of 5,000 reviews of a book called The Strain, which I'd never heard of before I did this project, but apparently it's a very popular book. It's sort of a young adult horror thing, I think. And the 5,000 reviews are, let's say, 100 words each. So we're talking about 500,000 words of text, which is longer than the book itself, so nobody got time for that. But we'd like something a bit richer than 3.8 stars out of 5. So there's surely there's some middle ground here, and that's what I'm claiming this is. I pull out here 12 or so sentences that are representative of the review. How did I do that? Well, the first thing is I fitted the topic model to the overall corpus of Amazon product reviews. Then I used that as the lens through which I looked at the individual set of 5,000 reviews. Having done that, I can now say, well, topic 1 and topic 4 and topic 8 are important, but I want to say something more humane than that. So rather than saying it like that, what I'm going to do is look for sentences that at the sentence level are dominated by topic 1, topic 4, and topic 8, if that's what I said. So I extract out those sentences, and that's how I show them. So you can quickly get an idea. In the time I've been saying this, you guys, I'm sure, have read this and now know what this book is about. I'd argue that this is a more humane visualization of text. Text is not numerical data. It's a square peg, round hole, to try and present it as such, in my view. But there are a couple of problems with topic modeling, which brings us on to the second algorithmic approach I want to talk about. Topic modeling, just like word clouds, ignores word order. The first thing we do with these documents is put them through a blender and forget the fact that documents have order. Sentences certainly have order. A sentence in which the word good is preceded by the word not means something very different to one where that doesn't happen. Word order is important, but obviously a document also has like longer range rhetorical structure. The things that occur at the start are, generally speaking, more significant than the stuff in the middle. Perhaps the stuff at the end is important as well. By putting our document through a blender, we lose all ability to learn from the position in the document or the grammatical or rhetorical structure. So we'd like to retain word order. We also like to retain more meaning than we do. I mentioned with the word cloud, there's no way you can run that word cloud in reverse and regenerate the document. You certainly can't do it with a topic model. A topic model reduces a document to 100 numbers or whatever. There's no way to run that in reverse and rebuild the document. It's extremely lossy compression. Perhaps there's some middle ground that's less lossy, I guess. And the breakthroughs that I want to talk about for both these problems, word order or document order and word meaning, come from recurrent neural networks. So for word meaning, which we'll start with, I'm going to talk about something called word-to-vec. Word-to-vec is perhaps the most famous early example of language embedding based on neural networks. We'll talk about what a language embedding in a second is, but I want to define the word-to-vec problem. Word-to-vec is this. It's a very, very strange supervised machine learning problem. Supervised machine learning means you have examples of the right answer and you want to learn how to get from question to right answer given a bunch of examples. The question here is, given a word, can I predict the words most likely to immediately precede and follow that word? So here I'm going to learn with one training example. The training example is the sentence, waffles are great. If R is my input, I want to build, that black box wants to be an algorithm that assigns high probability to the word waffles and great, because in my training set, those are the words that precede and follow R. You'd obviously want a more diverse training set than just that one example with a much larger vocabulary, but that's the basic idea. We want to predict context. This probably seems like a really weird problem to care about. The reason we care about it is the solution, post facto, it turns out the solution generates something very useful almost incidentally. But why was this a fruitful problem for deep learning people to solve back in 2012, 2013? The reason comes from intuition given by the English linguist John Firth back in the 50s. He said, you shall know a word by the company it keeps. And what I understand that to mean is that if you are able to associate words with the words they occur alongside, just in a statistical sense, if you are able to say that the word are occurs alongside the word waffles and great, you have in some sense learned something about what the word are means. At least that's the claim. Turns out that for our purposes, it's true, that claim, and here's why. We build a neural network to solve the word-to-vec problem, this predicting context. I'm not going to talk about how neural networks work, but fundamentally it's a horrendous black box, and we don't want to get into that. But what we do, word comes in, context comes out. The black box is doing something magic. We reach into the black box and pull out a word vector. As an incidental, like almost side effect, the black box is producing a sequence of numbers by which it's representing that word. So that sequence of numbers might be 100 numbers long or 1,000 numbers long that says when the word are comes in, first thing I'm going to do is turn it into that list of numbers. That list of numbers is chosen to be a good solution to the context problem, but why is it relevant? Well, I said it's 100 or 1,000 numbers long, and indeed it is. But let's imagine it's just 2 numbers long. So we can treat these 2 numbers as positions on a Cartesian plane like this. And this is where you find the words France, Germany, China, and Paris, Berlin, and Beijing on a Cartesian plane. And you can see here 2 things. One, words that are semantically similar are close together in this plane. That's the first thing. The second thing is that, for example, the distance and the direction I go to get from China to Beijing is the same or very similar to the distance and direction I go to get from France to Paris. Not only does location seem to have something to do with meaning, but also direction and distance has something to do with meaning. That's extremely vague and hand-wavy, I know, but you can see here that, assuming what I've claimed is true, we've solved the analogy problem. China is to Beijing as France is to Paris. We didn't set out to do that. We set out to predict context. What other problems have we accidentally solved here? It turns out we can use these word vectors for all sorts of machine learning problems involving text. That's how we're going to retain more meaning using word embeddings. The other problem I mentioned is word order or document structure. Traditional machine learning struggles here for a really mundane reason, which is that a typical machine learning model expects a fixed number of inputs. Let's say I built a model to predict how you voted, and it might consider your gender, your income, your location, all these things. But let's say it considers only those 3 things. I can't then give it an additional piece of information to help. I certainly can't give it the essay you wrote for your college application, which is an unknown length in advance. I have to give it the same 3 things every time. For image classification, that isn't the end of the story. Of course, images are different sizes, but you can rescale them in Photoshop. There are algorithms that will rescale images whilst retaining their meaning, I guess. There are no such algorithms for text. You can't crop off the first 1,000 words of a document and expect it to mean the same thing. You can't compress a document in that way. So what we need is a machine learning algorithm that can take in input of arbitrary, unknown, and advanced length and give out output of arbitrary, unknown length. The solution to that problem is recurrent neural networks. This is a cartoon of one. The black boxes are neural networks, and the recurrence comes from the fact that we chain these neural networks together in sequences, and that allows us to do machine learning with sequences. Sequences are things like time series or text. So we're in business. We can apply the techniques of machine learning to text now. And the way we're going to do this is train a supervised machine learning model to learn to identify what sentences are important to a document. We're going to teach a machine learning system an idea of salience. And we're going to give it the best possible chance of doing this job by retaining meaning using word vectors and retaining order using recurrent neural networks. When we do that, to cut a long story short, we end up with this proof of concept prototype we built. This is a browser extension called Brief. So you're on a long article. In this case, the demo I'm showing you is a very short article. According to Instapaper, it's a 1-minute read up the top there. But what we do is we allow the machine learning system to identify which sentences it considers salient. This is a 15-sentence or so article, and it's chosen 5. If you only have time to read 5 sentences, these are the 5 you should read. You may even have read those 5 sentences pulled out on the left there, and you maybe take my word for it, this is a pretty good summary of the document. As a visualization strategy, it induces a couple of challenges, though. The first is you don't actually see it in this document, but imagine I'd extracted out a sentence that said, he went to Paris. If I just extract that out and show it in isolation, you're left wondering, who's he? You can do pronoun disambiguation to figure that out, but another way of doing it, and again I'd argue a more humane way of doing it, is showing what we show on the right, which is showing the sentences in context. And I can now scroll through, and the bits that the machine considers important jump out, and if I want to go deeper, I can look at the surrounding text. We also played with visualizing it the other way. Rather than emphasizing what's important, we looked at de-emphasizing what's unimportant. Using CSS3, I guess. I'm sure the author of this article would be horrified to see this. And I'm not suggesting this is this should be implemented in newsrooms up and down the country, but this is something that the machine has learned to do itself in terms of identifying those sentences. I showed you a tiny little 1-minute article. I'm not going to make you read this 8-minute article to convince yourself this is a good summary, but this is a much longer article, and it works equally well on those kinds of articles. So, just to summarize what I said word clouds are bad, and that's the most important thing. The visualization is really hard to use. Just perceptually, it places incredible burden on a human brain. It's just it's not very easy to use. And is that burden worth it? No. If you spend the time to figure out what the word cloud is telling you, what it's telling you is not very much. It's telling you which words occurred the most often. That is not the same thing as which ideas are the most important. Topic models are a more semantically meaningful alternative to that. It doesn't count words, it counts or measures the relative importance of topics. And that, I would argue, is what we usually mean more often when we're comparing documents. Language embeddings and RNNs allow, allow computers to operate on the meaning and structure of text. So we can bust out the traditional arsenal of machine learning tools to figure out or to teach the machine which sentences are most important. I went at a very, very high level through the algorithms, topic models, and recurrent neural networks. If you'd like to see more, go to that link, and then there's a link both to a more technical version of this talk I gave and further reading if you're interested on the algorithmic side of things. Thank you very much. Do you have time?